Hi, I'm Ben. I'm going to be talking about methods of achieving optimal model complexity in machine learning. As part of this presentation, we'll briefly go through gradient descent optimization, dimensionality reduction, subset selection, adaptive learning rate, and data augmentation. So gradient descent is one of the earliest optimization methods. It has been here for a while, and it essentially works in a way that you have variables which are the features you're learning from being updated iteratively in the opposite direction of the gradients of the objective function, which is the loss function. So thinking in terms of a linear regression where we have this function L theta as our loss function and model as our linear regression model where theta is the land feature. For us to optimize this algorithm, we would have to derive the rate of change of the loss function with respect to the land feature, so this gradient here, and then we update the land features in a negative direction to minimize the loss function. So based on the rate of change with respect to the land features, with an introduction of a learning grid value, we can adjust our land features by a certain amount. So essentially, in a visual representation, it happens in such a way, like for every iteration, assuming this is like our loss function, you see it's sort of like a mean square error where this is the the predicted output, and this is the original output, and then we take the difference to get the loss. So you have some sort of like a quadratic shape of an estimated loss if we attempted to like plot a brute force output. So this is sort of like the output every per step in the iterative manner. The other approach that you can use for optimizing your algorithm is dimensionality reduction, and this is applicable in scenarios where you have too many features and it becomes complicated to perform a classification, as it turns into a challenging task comprehending the feature importance, also establishing feature independence, identifying which features are correlating with others. So generally it becomes hard for you to work with such a data set to perform a classification. So this is where dimensionality reduction comes into play, and it's a way to reduce the number of training features by establishing a set of principal features, like the most important features for you to perform the classification. So there are lots of methods. These are some of the popular ones: principal component analysis, the generalized discriminant analysis, and linear discriminant analysis. So briefly about the principal component analysis, essentially there are three main steps. So first, you just standardize your data to sort of like reduce the variance, and then compute the covariance matrix to sort of get like the idea of how far each feature value is deviating from the mean by comparing it with the other features, the neighboring features. And then after that, you compute the eigenvectors and eigenvalues from which you can identify the principal components. Next, we have subset selection, and this is typically applicable for linear models such as linear regression or logistic regression. So what happens is you experiment with a group of features. So there are two ways to do it. Like there's a forward stepwise selection and a backward stepwise selection. So for the forward one, we begin by approximating the response or the prediction with only one variable, and then we gradually keep on adding more variables and then generating the output prediction. So every time we add a variable, we only keep that a particular variable if it improves our model's accuracy. But if we add a variable that doesn't improve the accuracy, or one that drags the accuracy down, then we discard that variable. And then the backward stepwise selection is not very different. It's the same idea, but starting with a full model. So we begin with all features, and then we go on taking away one feature at a time. So if we take away a feature and we realize that our accuracy drops due to the elimination of this feature, then we bring that feature back. If we take away a feature and the accuracy improves, we completely discard that feature. And the other method of optimizing the algorithms, which is a popular one, is adaptive learning rate. So this is sort of an improvement to the gradient descent method. So there's a lot of methods that use gradient descent underneath to perform optimization. So this adaptive learning rate optimization method was introduced to sort of improve on these ones, and the basic idea is that your learning rate parameter keeps on changing dynamically. So you have like dynamic learning rate depending on how well the learning of your model is progressing. So that means that the stepwise parameter, this factor, but the step we make at every iteration of the gradient descent is no longer like a constant learning rate, but rather something that depends on the parameters. So some examples include AdaGrad, Adam Optimizer, and the RMS probe. And then lastly, we have data augmentation. So this is a method to essentially enlarge your data set, but it can actually help you in scenarios where you have a relatively small data set, especially for computer vision applications. So when you have a small data set, you can introduce, you can diversify your data set by using data augmentation techniques, and this way you have more meaningful data for your algorithm to learn, and then that, so in turn that means this method is actually helping you achieve an optimal model that way. So some of the most popular techniques we have with data augmentation include rotation. So you can have like an image and then you rotate it to get a variant, then you can flip it or scale it, like zoom in a bit, or crop it, just get just like getting a section within the image, or translating it along the X or Y axis by moving it, and then lastly by adding a Gaussian noise. So there's way more techniques of data augmentation, but for the purposes of this presentation, this is what I captured. Thank you.